Welcome to Unit 8, Inference for Categorical Data, chi-squared. All right, in this video, we're going to cover topic 8.2, setting up a chi-squared goodness of fit test. So at the end of the day, this test is a lot like all the other significance tests that we've been running in this course. And there are, of course, 4 steps. We typically look at the first 2 steps, the hypotheses and the conditions is getting it kind of set up. And then step 3 is really doing the work. And then step 4 is making a conclusion. So this video is just setting it up, which we're going to look at topics or steps 1 and 2 in topic 8.2. And then in topic 8.3, the next video here, we will actually finish it off by doing steps 3 and 4 to finish up the test. All right, so let's first remind ourselves, in the last video we learned really what a chi-squared test is all about. And it's really all about looking at categorical data, not just one particular category, but the entire categorical data or the entire categorical variable. So let's just talk a little bit about a goodness of fit test. And when you are presented with a problem, how do you know? I mean, gosh, we've learned so much by now, means, proportions. How do you know you're working with a goodness of fit test? So here's 4 things that kind of point you to it being a goodness of fit test. Number 1, you have categorical data in front of you. You have data that comes in that comes in the form of words. There's different categories that any person in the sample could fall into. Each individual falls into a particular category. I like chocolate ice cream. I like vanilla ice cream. I like strawberry ice cream. I'm going to fall into the category that that represents me. The other side of a goodness of fit test is there's only one categorical variable. But there could be many categories, strawberry ice cream, banana ice cream, chocolate, whatever. Right? The list goes on, right? There's many different categories within that one categorical variable of favorite flavor of ice cream. And the data needs to be shown in counts. So what you're looking at in each category is simply how many people were counted that fit into that category. So I counted 22 people that love chocolate ice cream. So you're going to see a 22 underneath chocolate. I counted 32 people that like vanilla ice cream. So you're going to see a 32. So those are counts, the number of people that we counted that fit into each category. And finally, the big thing that recognizes this as a goodness of fit test is that the goal of the problem is to see how well the sample data fits with some given or described distribution from the population. So that's the whole point of a goodness of fit test. We want to see how good does our data fit with what maybe we were told was true for the population. So do we fit the data or do we not fit the data? So when considering a distribution of proportions for one categorical variable, the appropriate test is a chi-squared test for goodness of fit. Okay? All right, so let's make sure we understand the big idea here. So a sample distribution of a single categorical variable is given to us in the form of counts. Remember that one variable can have many possible outcomes. I can't stress that enough. These counts given to us from our sample are what we observed. So we observed what you're going to see in the table. And again, this will all be given to you in any problem. We are then also given a statement about what the distribution is expected to be. So you're going to not only be told what the observed data was, but you're going to be told what the data was expected to be. This statement can come in the form of words or maybe in a distribution of some kind. The goal is to determine how well our observed counts fit with what was expected. And I know this may still seem a little bit new and a little bit confusing, but once we get through a couple of examples, it will make so much sense, trust me. All right, so again, 4 steps to goodness of fit test, just like there's been 4 steps to every test we've learned so far this year. Step 1 is to name the test and give the hypotheses. Step 2, check the conditions and get your counts. That is the observed counts and the expected counts. Step 3 is to do the work to find the p-value, and step 4 is to make a conclusion based on that p-value. So the good news is you should recognize, p-values? Oh, I get that. That's easy. I'm simply going to compare my p-value to my level of significance. If I'm lower, I'm going to reject the null. If I'm higher than the level of significance, I'm going to fail to reject the null. Good news is none of that is going to change. So a lot of these steps do look very, very familiar. Now, the best way to truly understand them is to really kind of see them in motion, see them in an actual problem. So remember, this video today is going to cover the first 2 steps, which is just kind of getting it all set up. And then topic 8.3 will explore finding the p-value and making a conclusion. All right, so let's look at an example here. All right, so here's an example called I Only Have Eyes for You. So data from a random sample of 450 adults in Ohio shows the following breakdown of eye color. So notice one categorical variable, eye color, many different categories. I see counted data. 370 people were counted to have brown eyes. 5 people were counted to have green eyes. There's only one categorical variable. I don't see 2 or 3. I don't see gender. I don't see high school, middle school. I don't see US versus Canada. I see just eye color. One sample, eye color. All signs that are pointing to a goodness of fit test. Now, here's where the fit comes in. For a long time, researchers have believed that nationwide, throughout the US, the proportion of eye colors has followed this distribution. 10% blue, 78% brown, 2% green, 5% hazel, and 5% amber. So this is what we were expected to see, right? This is what we were expecting to see. And we want to see how well does our data fit with what was expected. And if it fits pretty well, well then, you know what? I guess Ohio's no different than the rest of the nation. But if it doesn't fit well, if it's too far off from what was expected, that's when we might see that maybe this distribution that's true for the nation is no longer true for Ohio. So that's where the question comes. Remember, the fourth way to identify goodness of fit is read the question. It says, does our sample provide convincing evidence that the nationwide proportions understood by researchers are no longer valid in Ohio? So we want to see how well does the numbers from the nation that we see right here as the expected values, how well do they fit with what's in Ohio? And if they don't fit, well then I guess Ohio, for whatever reasons, different. And that's the whole point of the test. All right, so step one is naming it and giving those hypotheses. So this is going to look a little bit different than it has in the past. So number one, the name of this is a chi-square test for goodness of fit. Again, you got to recognize one categorical variable counts. I want to see how well that one categorical variable fits with some given distribution. That's how you're going to recognize this is a goodness of fit test. Now, here the null and the alternative hypotheses that we have seen so many times before are all words, no symbols, no numbers. So the null hypothesis specifies the null proportion for each category, right? And the alternative hypothesis, at least one proportion is not specified in the null hypothesis. So so let me kind of backtrack for 1 second. You can use numbers if you wanted to, but I actually don't recommend it. It's easier just to use words. So basically the null is that, hey, everything is the way that we thought it was. The distribution is totally fine. The distribution we thought was true is okay. And then the alternative is, whoa, something's not fitting. Even if it's at least one of those values, it doesn't seem to fit. So essentially it's this. The null hypothesis is the distribution of the categorical variable is as we expected it to be. Okay? Be more specific of an actual problem. And I'll show you that in the example that we're working with the eye color here in a second. So the alternative hypothesis is that the distribution of the categorical variable is not as we expected it to be. Because that's what we're trying to see. We're trying to see, is the data no longer valid, right? Is the distribution that we said no longer valid? So the alternative is what we're looking for, and then it's not what we expected it to be. So let's go back to the eyes problem here. So in words, the null hypothesis would be the distribution of eye colors for Ohio adults are consistent with what was expected from the researchers' claims for the nation. So the null is that, hey, everything's the way it should be. The distribution that we saw is the same as it is in Ohio. It's consistent with it. Listen, there's always going to be those subtle differences. Hey, that's the world we live in. But again, the null says, hey, listen, they're consistent enough that what we expected is true in Ohio. And then the alternative is that the distribution of eye color for Ohio adults are not consistent with what was expected from the researchers' claims for the nation. Okay? Now, that's what I recommend. I recommend using words. I really think that using words is simple, it's fast, it's convenient, it makes the most sense for what the question's asking. But you actually can use symbols if you wanted to. But again, I'm showing you this, but I don't recommend it. So the null would be that the proportion of all people that have blue eyes, 10%, just like we read. Brown, 78%. Green, 2%. Hazel, 5%. Amber, 5%. Hey, everything is the way that we said it was. There's your null, right? And the alternative is that at least one of them is wrong. At least blue, brown, green, hazel, amber. If at least one of them is too far off from what was expected, that's when we're going to go ahead and reject the null and keep that alternative. All right. So let's talk about number 2. Step 2 is actually really, really easy. We got to just check our conditions for a chi-square test to actually work. So first is that, of course, this just sounds very familiar, we need our sample to be random to avoid bias. Number 2 is that the sample size must be under 10% of the population from which it was drawn to assume independence. I feel like, as a good teacher, I always got to explain why that condition is. Remember, think of a small bag of Skittles, maybe only 50 Skittles. And if you take out 10, eat them, take out 10, eat them, you have taken out such a big chunk of that bag that eventually you're going to reach in, there's no more Skittles left. And, maybe you took out 5 red ones the first time. Well, boy, you have significantly changed what is left in that bag. So that means that every sample is certainly not independent because you're taking out so many. But if you go to the M&M's, M&M's, if you go to the Skittles factory and there's millions of Skittles and you take out 10, eat them, take out 10, eat them, take out 10, eat them, trust me, you're not really changing any of the samples. The samples are still independent because there was such a vast majority of Skittles to begin with that even if you take out 10 red ones, you haven't really changed what was left in that huge vat of Skittles, okay? So that's where we say that, listen, if you don't replace, you are essentially changing what's going to happen next. And that violates independence. But that's where the 10% condition comes in and says, listen, as long as your sample is under 10% of the population, you're not going to change it enough for it to be that big of a deal. All right. Finally, the sample size must be big enough, which means that the expected counts must all be at least 5 or larger. Now, we still got a little bit of work to talk about what we mean by expected counts, but I think it'll be actually really, really easy. But at the end of the day, all of the expected counts have to be 10 or larger, not the observed counts, just the expected counts. So we need our observed counts and our expected counts. That's, we can't officially check off condition number 3 until we find the expected counts. So we're going to make a nice and simple table of values, and the observed counts for each category will be given to you, typically in a table. So note that the observed counts are always given to you. We just simply have to calculate the expected. It's really simple. Check this out. All right, so first let's run through the conditions for our eye color problem. The sample of 450 people was selected randomly from the population of people in Ohio to avoid bias. 450 adults is certainly less than 10% of all adults in Ohio to assume independence. And there are 5 or more expected counts in each category. But let me show that. I'm going to make sure you understand that. So you'll notice I made a nice little chart here. So the first row right here is what we were observed in our sample. 40, 375, 20, and 15. Now the bottom are the expected counts. Now how the heck did I get those? I used the proportions. So I went back here and I said, okay, 10% of people were supposed to have blue eyes. So I took 450 total people that were in our sample, and if 10% of them were supposed to have blue eyes, then that's what I should expect to see there. So 10% times 0.1, 10% times 450 is where I got 45 people that I expected to have blue eyes. Then I did 78% of 450 that were supposed to have brown eyes. So 78%, 0.78 times 450 is 351 people that I expected to have brown eyes. And I just continue to repeat this process all the way down the line. 2% of 450 were supposed to have green eyes, so 0.02 times 450 is 9. 5% for hazel, 5% for amber, so 5% of 450, 0.05 times 450. So those numbers would actually be the same, so it'd be 22.5 for both hazel and for amber. So now, we finished step 1 and step 2, right? So now we've officially said that all of these expected counts are all bigger than 5 or larger. So we're good to go with all of our conditions. So now, I don't want to spill the beans too much for what we're going to learn in topic 8.3, but now we have to decide, are these numbers so different? Is one of these numbers so far off that we can officially say that Ohio's distribution of eye color is not consistent with the rest of the nation? I mean, just using your old grandmother's eyesight, blue, 40, 45, really not that close. Green, 5 versus 9, that's not far away. Hazel, 20 versus 22.5, that's really close. Even brown, 370 to 351. Okay, so, obviously the point is, I really want to emphasize that, notice we're not seeing any of them match up perfectly. None of them are fitting perfectly, right? That's why it's called a goodness of fit test. So our job is to determine is, do they fit good enough? Or are they way too far off? And again, that's what we're going to learn about, how to figure that out. Because you don't just base it on, oh yeah, 5 verse 9, yeah, that's way far off. You don't just base it on your own personal feelings. It's got to be based on a statistical process. And that's where steps 3 comes in when we get that p-value. All right, let's look at a whole nother example just to see all of these steps in play one more time. So where do deer live? Wildlife experts have long believed that the number of deer that live in a specific habitat of a forest is proportional to the size of a habitat. That makes sense. If a habitat size is bigger, then more deer will live there. Makes a lot of sense. However, some researchers don't believe that to be true. They think deer prefer certain habitats regardless of size. So for example, if there's a really small region of the forest that just deer really love, then maybe even though it's small, a bunch of deer live there. Okay, I could see that being possible. So to test this idea, wildlife researchers did some aerial surveillance of a forest with 4 specific habitats of deer. They recorded the proportional size of each habitat and the number of deer living in each habitat. So here's our data, right? We have 4 different habitats, and we observed 44 deer living in habitat 1, 124 living in habitat 2, 35 in habitat 3, and 147 in habitat 4. So 350 total deer. But we also looked at the proportion of the forest. So habitat 1 had 10.5% of the forest. Habitat 2, 35.4% of the forest. Habitat 3, 27.8% of the forest. And Habitat 4, 2.63% of the forest. Now remember, it has long been believed that the proportion of the forest is represented to the proportion of deer that live in that part of the forest. So that's where we're going to kind of have our hypotheses come in here, and you'll see in a second. So the question is, does this data provide convincing evidence that the number of deer living in each habitat is not proportional to the size of deer in that habitat? And it wants us to use the 5% level. All right, so step 1, naming the hypotheses. So this is a chi-squared test for goodness of fit. How do I know that? Well, there's only one categorical variable. Where do the deer live? Habitat 1, 2, 3, 4. 4 categories, 1 categorical variable. That's it. It's not like I was looking at females versus males or a certain type of deer versus another type of deer. I'm not comparing 2 different states. I'm looking at 1 categorical variable. That's it. All right, now, the null is that the distribution of deer that live in a specific habitat of a forest is proportional to the size. So the null is what was long believed to be true, and that's that the proportion of deer is equal to the proportion size of the habitat. Where the alternative is what we're looking for. We're looking for the distribution of deer that live in a specific habitat of the forest is not proportional to the size of the habitat. Now I want to point out something awesome here. This is really cool. And this is always going to be the case with chi-square tests. You could literally copy and paste the null on the alternative. The only difference is adding the word not in the alternative. It's literally the exact same sentence. The null says that they are proportional, and the alternative says they're not proportional. And that's always going to be the case. They're really easy to write. All right, now let's move on to step number 2. The sample was, of course, selected randomly to avoid bias. 350 deer is less than 10% of all deer to assume independence. You know, in a large forest in Pennsylvania, there's probably going to be thousands of deer. And there are 5 or more expected counts in each category. But I really can't officially check that off until I get my expected values. All right, so let's make a nice little table here. And the AP graders love it when you make a little table to organize yourselves. So right here are my observed values. These are the values that I observed. The helicopter that took these aerial photos found 44, 124, 35, 147 deer in each habitat. Now the expected. So remember the null. We always assume the null is true, right? And the null says that the proportion of the forest is equal to the proportion of the deer. Okay, so if habitat 1 is 10.5% of the forest, then 10.5% of the deer should live there. So 0.105 times 350 deer, there should have been 36.75 deer there. Now, I know that you can't have 36.75 deer, but it's an expected value. It'd be an average in the long run, so we actually are totally okay with leaving a couple decimals here. I usually round to 2. All right, habitat 2, 35.4% of the forest. Well, if the null's true, then 35.4% of the deer should live there. So 350 deer times 0.354, 123.9 deer should be living there. Habitat 3, 27.8% of the forest. Well, if the null's true, 27.8% of the deer should be living there. So times 350 by 0.278, 97.3. Same thing with habitat 4, 26.3% of the forest. Therefore, 26.3% of 350 deer should be living there. So again, I'm looking at these numbers and I'm saying, well, habitat 1's pretty close, 44 versus 36.75. Habitat 2 is, holy cow, really, really close. But now I'm looking at habitat 3, and man, 35 is what I observed, 97 was what I expected. That seems kind of low. Habitat 4, 147 observed, only 92 expected. But again, you don't make the decision based on your personal feelings, like maybe my grandma would do. You make the decision based on statistics, right? Just because you see what you believe to be a big or small difference, well, you need to actually run the test, find that p-value to actually figure it out. So that's what we're going to do moving forward in topic 8.3. All right, so setting up a goodness of fit test is really fairly easy. I mean, it really, really is. You just need to name it, check the conditions. Oh, don't forget to give those hypotheses. Check the conditions and get those expected counts based on what the scenario lays out. So read the scenario over, figure out what it's saying to you, and that's how you create your hypotheses, and that's how you calculate your expected values. And then next step is to find what we call the chi-squared number, and that's going to be using the expected and the observed counts. It's actually really, really easy. And then we'll move on to creating the p-value as well. All right, guys, that's it. See you in the next video.